Bien, c'est un plaisir de souhaiter Caroline Antos, qui va lancer cette année de séminaire. Elle va nous parler de l'utilisation des exemples en mathématiques. Elle va parler en anglais, mais j'ai fait cette introduction en français. Over to you.
Okay, thank you very much. Thank you for the invitation. I'm very happy to be here. Unfortunately, my French is basically non-existing, so I will talk in English, and it would be great if you could ask questions in English as well, because I just won't be able to understand them if they're in French. I could follow a little bit what Tim was saying, but you know, that is the level that I have. I can recognize my own name. Okay, good. So this is a philosophical talk, but it's philosophy of mathematics. So I'm a mathematician by training, but I have switched to philosophy around 10 years ago, and I've been working in philosophy of math since then. There is not a lot of, like technical things in this talk that you have to understand. There will be some coming up, but this is really just as an example, and you will be able to ignore the technical details and still be able to follow this talk. So I hope this will be interesting to anyone here. Okay, good. So this is about a certain type of reasoning in mathematics that is something that is perhaps not usually thought about, at least from the philosophical side. It's reasoning with specifics. And I will give you a little bit of background, and then I'll get into what I'm doing here. This is a little bit work in progress still, because I have just started to work on this, and everything that you can tell me about your own opinions about this will be very helpful to me. Okay, good. So the background here. So usually generalization and abstraction are considered to be kind of the most powerful tools that we have in mathematics. And I'm totally fine with that. I just want to say this up front. It's not that I have anything against generalization and abstraction. That would be strange for being a mathematician. But there are parts of these processes that I think have not been looked at a lot from the philosophical side. And these are the starting points. A lot of times when we generalize or when we abstract in mathematics, we start from specific examples or instances. And these starting points are usually not very much considered in philosophy, because they are seen as something that is nice to have for developing things. But then when we are there, when we have, like the real mathematics that we have developed, then we can actually dispense with examples. So if we have a proof, we have the proof, and we don't have to look at examples for this. So they are usually seen as something like helpful illustrations or heuristic tools with which we can do stuff, but then they are not further considered. So what you can find in the literature, even if people study mathematical practice, you have very much a focus on proofs and definitions, and rightly so, because they are important parts of mathematics, but examples are not really studied at all, and this is what I want to start with in this talk. So, because when we look at mathematical reasoning, so the things that we do when we do mathematics, examples are kind of a constant part of what we're doing. So this is just a very basic list of things that we have. We have counterexamples. We can test if a definition fits a concept by looking at specific examples. We use them as first answers to queries. So does this hold, yes or no? Let's look at some examples to see how it works. We have it when we want to argue for relevance of a concept. So this is a natural concept because it matches things that we find in mathematics, some mathematical objects that we have. We use it when searching for proofs and all of this. So we have reasoning in mathematics that is based on examples. And to quantify this a little bit, so this is a study that has been done on this mini polymath project that probably you've heard about. And here they tried to categorize the things that people used when they were searching for a proof. So this is, was a problem was posed, and then there was kind of a mass collaborative aspect on the internet, and they tried to prove this, and these were the things that they used And you can see that a rather big part of this is the use of examples in trying to come up with a proof here. So this is something that happens. It is part of mathematical practice, and this is the main reason why I want to look at this. Okay, so this is the overview. The main goal, and I'm not, I'm not going to finish this goal in this talk. This is something that I'm working on right now. But what I want to do is explore the epistemic role that exemplary reasoning has in mathematics. And here I want to talk about very basic things. So what is this kind of exemplary reasoning, what I'm actually talking about? Then I want to look at uses of examples in mathematics, because I think this is very much context dependent, dependent on the use that we have in mathematics. And then I want to look at this from a philosophical perspective, like embedded into things that we do in philosophy of mathematics. And this is the last point. I want to see if exemplary reasoning is epistemically relevant in mathematics. Yes or no, and I want to say yes, but we will see how far this goes. Okay, good. So what is this that we talk about when I say something like exemplary reasoning? What does this entail? Well, very basically, this is based on exemplification. And let's start with an example, because that's appropriate. Look at this very basic example that we have. 3 is an example for an odd number. So this is something that you could find in mathematics, something like that. Okay, so here you can see the structure of exemplification. There is something that does the exemplifying. This is 3. And the thing that gets exemplified, this is, in this case, odd number, the concept of odd number. And what we usually have is that people focus very much on the thing that gets exemplified, so the concept behind it, because this is the more abstract, the more general thing, this is the thing that we work with. And people don't look as much at the example itself. It just seems to be a vehicle for, like doing something with a more abstract concept that we have here. And this is what I want to do. I want to kind of shift this focus a little bit away from what is exemplified and look at the example itself and the uses that it has and what it does in mathematical reasoning. So this is just to get the right perspective of what I'm after here. Okay, so I think one of the problems why people might think that examples or exemplification is not that interesting is because they have a quite narrow understanding of what examples can be in mathematics. And what I want to say here is that this is much more complex than one might think from kind of first looking at this. Usually examples in mathematics are understood as having the form that we saw in our 3 is an example for an odd number example. So we have kind of a fully specified mathematical object, 3, and it is an example of a concept like odd number. But exemplification in mathematics is much more complex than that, and I want to just look at kind of 3 dimensions of what this entails. So the first is that examples don't have to be fully specified, and in a lot of times they aren't fully specified, like the sense like pointing at one mathematical object. The other is that it doesn't even have to say something about objects themselves. It can be, the example can consist of something else than an object. And the third thing is it doesn't have to be a mathematical object that is being used when we point at an example. And let me say something regarding every one of these things. So when looking at specification here, what I mean by that is the following. So we have fully specified examples where we look at a specific object, like 3, for example, and I would even count something like this function as something like that. The function as a fully specified object. So I think everybody would say, well, this is an example, but of course we also have something like partially specified examples, and they are used as examples, and they are usually, I would say, accepted as being an example. So if I would say something like basis of a vector space is an example for a linearly independent subspace, people would accept that as an example. They wouldn't say, no, if I want to have an example, you have to give me this specific basis or something like that. Or if I want to say something, this is a model that satisfies CH, then I can give some model that satisfies CH. This is not fully specified, it is just partially specified in that it satisfies CH, for example, or an equation of a certain form. So I think mathematicians using examples don't even think about this fully specified, partially specified thing. It's just something that happens. The third thing is something that is a little bit different. the philosophical literature, you find this being called arbitrary examples. And this is just what happens when we, for example, do induction or something like that. If we say something like, let n be an arbitrary number. Of course, n is not fully specified because it's an arbitrary number, but it can still be used as a kind of example for something. We will see an example using this example. I'm sorry, the word example will come up a lot in this talk. Later on, but this is something that happens as well. And this is called arbitrary example because it's a little bit different than the others. Like one feature of these arbitrary examples is what we use them for, namely like as a standing in for a range of different mathematical objects that we can talk about. And I would count this as an example as well because this comes up in exemplification. And of course, this is not specified at all in a certain sense. If we just look at the natural numbers, then saying let n be an arbitrary natural number, this is not specified. Okay, good. So that was the specificity complexity that we have. Now looking at the question if things have to be objects or not. So they don't have to be singular mathematical objects. Examples are often something like a scenario or a strategy or a method or something. And they exemplify classes of things or situations or something like that. So here we have an example of this from an algebra book. And if you read this, so this is one of these things where you don't have to understand all the technical details that are in there. Just look at what is done here. So we're looking at something that is called an n-dimensional vector space over a field of real numbers. And then we do some things. We actually define something, this cube of length 2 epsilon. And then we say something about what this thing that we defined does. So it has it satisfies some conditions. And then we say that the thing that we just partially constructed here is a vector space. And this is a topological space with the cube as a neighborhood basis. This is used as an example for a neighborhood basis, but actually it does a little bit more in case of if you would want to look at exemplifying. What it does is it kind of describes a scenario. So the example itself is a scenario. And it's not only an example for a topological space and so on and so forth, but it's also an example for something else, namely a neighborhood basis. So within the scenario, we have kind of examples for different mathematical concepts that we have. And what we also have is not only examples for the involved concepts, but you also have an example of how these concepts are related to one another. So this is kind of a more complex example that does not have the structure of being one mathematical object. It just looks at different mathematical objects and the relations that we have between them. And here actually we also have these arbitrary examples coming up. So we have something like the vector space that is given for an arbitrary n. And these are, I would say, the more usual things that come up if you really do mathematics, because something like 3 as an example for an odd number is basically not that interesting. I mean, when you have something, in a lot of times you're constructing these kind of scenarios. Okay, so, and the last kind of dimension that we have when we look at examples is something that are not mathematical objects, but meta-mathematical objects. So of course, example giving can also be something like exemplary sentences or exemplary proofs or definitions or something like that. So these are not mathematical objects because it's a sentence, it's a linguistic object. And they can exemplify different things. They can exemplify collections of the same thing. So a sentence can be an example for a group of sentences that shares a certain property or something like that. Or it can be an example for scenarios or methods or applications. And of course, these 3 dimensions are not separate in a sense. If I give an example, different of these components can come up in this example. Okay, so let's look at this here. So this is one where we have a statement that is used as an example for something. So we say something about a certain theorem that we just proved. And then we say that it holds for something which the corollary does not satisfy. And this is, so again, don't worry too much about the technical details here. Oh, this too should be an arrow, and Amina should probably recognize this. So here we have a statement. This is an example for a non-equivalence. of two propositions that we look at. And it's also an example for a statement that is sufficient for another statement. So the statement itself is the example for something. And this is the focus that I have. I want to look really at the example that is given and not so much what it exemplifies, but the example itself. Okay, so we have kind of a great variety of examples here. In any case, what we do is we have then exemplary reasoning as reasoning based on exemplification. And we have just seen which various things we can have with respect to exemplification. So example giving is part of this exemplary reasoning. Of course, that means that it uses specification, but it's some kind of higher order specification. It doesn't really mean that the example has to be fully specified itself. It can be something like an arbitrary example as well. It doesn't mean that every time I use an example when doing something in mathematics is exemplary reasoning, because there can be something like illustration or something like that behind it. It just means that from this example we draw some kind of a conclusion about this. And this is, I think, important to see because reasoning always has this conclusion focused part. So for instance, if we look at something like the sentence 3 is an odd number, that does not necessarily has to be an instance of exemplary reasoning, because it can just be that we want to illustrate the concept of odd number or something like that. But mostly it will also involve some type of conclusions that we draw. For example, we want to show that a concept that we have is not an empty concept, so that there is something that actually satisfies this concept. Or we want to show that the specific object that we're looking at has some certain property. And these, I would say, are instances of exemplary reasoning. So we draw some kind of conclusion from these. Okay, so this is also why I would say that even if in example giving we sometimes have objects appearing that are not mathematical objects themselves, these are still mathematical examples because they are used in mathematical practice. And what this tells us, I think both of these things, seeing what uses the example has within the reasoning that I'm doing, and looking at where they come up, this means that exemplary reasoning is use sensitive. So it really depends on the way in which it is used in mathematics. So what do we do in mathematics when we use examples? And this is why I think we have to take a closer look at the use of examples in mathematics. So what is the goal for which we do something like exemplifying things? And I don't think I have time here to do too much, but let's look a little bit at the uses of examples. And of course, I mean, if you're working in mathematics, you will come up with a lot of other uses as well, and I would be very happy to hear about them. So one of the big things that it is used for is illustration. This is also why we find a lot of examples in textbooks or in teaching, for example. But illustration can mean different things. It doesn't just mean to help you to visualize something, like showcasing that something holds or something like that. It can also be something that is, in a certain sense, a little bit more substantial, philosophically seen at least. And this is what I want to say when I say examples are used to produce understanding. Understanding is a philosophical concept that many people have talked about. There are different ways of approaching what understanding means. What we are doing here is we consider a specific account of understanding that was developed for mathematics by Jeremy Avigad, who is a mathematician and philosopher at Carnegie Mellon, I think. And he has written on this, and it's interesting because he does not talk about examples specifically or the way in which examples are used, but just the way in which he talks about an ability account of understanding makes examples kind of come up organically in what he's doing. And I want to have a little bit of a look at this because I think it very nicely illustrates how examples are used in mathematics. So this is the discussion he gives about what it means to understand a theory via abilities. So this is really an ability-based account of understanding. He says, suppose I tell you that my friend Paolo understands group theory, and you ask me to explain what I mean. In response, I made note that Paulo can state the definition of a group and provide some examples, that he can recognize the additive group structure of the integers and characterize all the subgroups, that he knows Lagrange's theorem and can use it to show that the order of any element of a finite group divides the order of the group, that he knows what a normal subgroup is and can form a quotient group and work with it appropriately, that he can list all the finite groups of order less than 12 up to isomorphism, that he can solve all the exercises in an elementary textbook, and so on and so forth. So what he's doing is he's giving a list of abilities and saying this is what understanding is based on. Being able to do these things, so having these abilities, means that he understands something like the theory. And of course, if you look at these abilities that he gives, a lot of them involve examples in a very heavy way. So providing examples or doing exemplification is something that comes in a lot here. So let's look just at some of these. So he starts by saying we have a definition of some concept, and part of the ability to understand it is to provide examples for this concept. This is more than just knowing the definition by heart, it really is understanding what it means. Okay, then two other abilities concern being able to work with standard examples that we have. This is what comes up. So this is also something that we will have a look at later on. Not only examples, but it's something that he calls standard examples. Sometimes he also calls them natural examples. And then some of the abilities that you might have is to work with these kind of canonical examples that you have in mathematics. So with the example of a specific theorem that comes up within a theory, and you can do something with it and you can work with it. He does the same thing for proof understanding. So the other one was theory understanding, and then he talks about what it means to understand a proof. And he comes up with kind of a similar list of abilities, but abilities that he now uses to say this: if you have these abilities, it means that you understand a proof. And in this list of abilities, again, examples come up very heavily. So he, for example, says, is give a natural example of the various phenomena described in the proof. Or calculate a particular quantity, or provide an explicit description of an object whose existence is guaranteed by the theorem. This is also something that works with an example, rather specific example. Indicate where in the proof certain of the theorem's hypotheses are needed, and perhaps to provide counterexamples that show what goes wrong when various hypotheses are omitted. Again, he's talking about examples here. So you can see what this means. So again, he does not say anything about examples specifically. They just come up in what he says when he says, we want to say something about theory understanding and about proof understanding. And I think this highlights very nicely how examples are used. So being able to work with examples is a big part of what it means to understand mathematics. If you understand the theory and if you understand the proof in them, you're really kind of at a high level of understanding the mathematics behind it. Okay, so this is something that is interesting. Another thing that I talked about now is that kind of examples are sometimes qualified in a certain sense to be more than just one example, something like we talked about natural examples and these things. And this is also interesting because formally, if I just have a concept, every instance of this concept is formally kind of on the same page, so to speak. So it is as good an example of this concept as any other that I can choose. So here you have 3 examples of odd number, and any one of these is as much an odd number as the other. But basically what you would do is you would choose 3 if you want to explain to somebody, like if you want to give an example for an odd number, more easily than others. And this is not just me saying this. Actually, there is a cognitive study that was done in the 70s, 80s, I think, where they presented people with several odd numbers, and then they should choose which one is an odd number and which one isn't. What they tested was in how much people kind of recognize something as a prototypical example of a concept. This was about a certain theory of concept that is part of cognitive science. And people always had a much easier time of saying 3 is a prototypical example of odd number than any of these other numbers that are there. Even if they understood what they have to check to see if it's an odd number, which doesn't, doesn't really depend on how long the number is. It should be equally easy to do. Okay, but if we look at mathematical practice again, usually what we do is refer to a quite small number of examples. If I give you an example of something, for example, of a group, you won't pull some random, complicated technical group out of the hat and then say, well, this is a good example for this. You will start with something that people can relate to, set of integers with addition, for example. If we want to say something like, oh, I want to teach you about, or I want to tell you what countability is, I won't give you some very strange ordinal number that has the cardinality of the natural numbers, but I will talk about the size of the natural numbers. So we have kind of usually in mathematics, a set of a small number of examples that we kind of go to when we do something. And these are often referred to as natural or canonical or standard or classical examples. And this comes, usually you can find this in textbooks or even in papers when people say something about this. And the ability account, as we have seen, actually recognizes this. So in a lot of these abilities that were given for what it means to understand something, he didn't just say, well, we know the definition of a group and we can give some example of this. What he actually says is we can give a standard example of this, or we can give a natural example of this. So what we can already see is that in the use of examples, we have some that are kind of especially salient. And they seem to carry more information than other examples, although formally they are all the same. Okay, so these have been some things that we look at when we want to look at uses. Of course, there are other uses besides understanding. Understanding is just one that I looked at here, but there are other uses of examples. One of them is to say that something is specifically natural or fruitful or useful. This is something where people use examples as well. So, for example, to say, we want to say that a new concept is natural, and what we would do as part of the argument to say that a concept that we introduce is natural, we would look at natural examples and then say, oh, this concept picks up kind of nicely this kind of natural examples that we want to look at in the context in which we're looking at this. If we want to say that a new theorem is useful, we can say something because it explains kind of a prominent phenomenon that we have in mathematics. So we, again, give an example of what we want to address, and we can say that the theorem is useful for addressing this. Or if we have a theory, we can say that a theory is fruitful because it allows us to study some canonical cases that come up in mathematics. Okay, so again, what we have is, it seems that the use of examples kind of is not the same for all the examples. So sometimes, oh, sorry, I thought I had it put down here, but it must be somewhere else in my slides. So some examples kind of carry more information than other examples. And it's what I would think is that these examples kind of are of specific epistemic value. And this epistemic value depends on the context in which it arises and in the context in which it is used in mathematical reasoning. Okay, so I hopefully this convinced you that examples and exemplary reasoning is something that is epistemically valuable in mathematics. Now, I started with this statement that it is usually not considered to be epistemically valuable. And this is kind of, this perspective or this view is embedded in a broader philosophical idea that we have when we study sciences. So if I want to say something like exemplary reasoning is epistemically not relevant in mathematics, if I would like to argue that, I actually don't, but people usually, I think, like from the outset would say something like that. This is sometimes, or this is, can be seen or can be better understood in a certain background idea that we have in philosophy. So what we don't want to say is, if we say that exemplary reasoning does not play a significant epistemic role, what this view usually does not mean is that these instances of uses of examples that I just gave you do not happen or something like that. They wouldn't say, no, this is not part of mathematical practice. It wouldn't make sense to make this argument because it just is part of mathematical practice. What they mean by that is that these things are not something that is epistemically relevant philosophically seen, because they say, well, these examples are helpful, but they're only helpful as something like heuristic tools. So in part of mathematical discovery processes like concept development or hypothesis formulation or search for proofs, we have them, or we have them for educational purposes like teaching and learning. But this is not what we are interested in. What we are actually philosophically interested in is a different context, not this context of discovery as it's called in philosophy, but the context of justification. And usually, so this, if you have a background in philosophy and philosophy of science, you have seen this distinction between context of discovery and context of justification. And one way of looking at this, this distinction is saying that what we are usually interested in when we look at things philosophically is the context of justification. So how do we know that something is the case? And in mathematics, we have a very nice thing of doing that, namely proving something. Yeah? So mathematics is a science where this context of justification can be very nicely addressed because we have something like proofs in other sciences. This is not as easy. And then these people would say, well, when we want to know if examples are really epistemically valuable or not, we are not so much interested in the context of discovery. That's nice and well, but this is something that we cannot really approach philosophically. What we want to understand is if they are important for the context of justification. And this nowadays is very much connected to the modern understanding of proofs, which is an axiomatic understanding of proofs. So trying to argue for this view, what one could say is examples are not relevant for what we think axiomatically style proofs are, because these are always general and abstract and not based on examples or exemplary reasoning. Let's look at a little bit at that historical outlook to see how this might have changed. So before this modern axiomatic interpretation of proofs, the use of examples was actually quite prominent in proofs, and basically nowadays people wouldn't accept a lot of these things as proofs anymore. So one of the person who did this was Euler, but also others, and he very heavily used examples to prove general theorems. He kind of proved a general theorem by just giving an example of how this worked or that this holds. It's not that he was, like too naive to understand what he was doing there, not at all. He also advised caution about choosing the right example, because the example had to be in a certain way that this doesn't lead into this proof by example fallacy that is there. So he knew that, but this did not lead him to saying something like, oh, we shouldn't use examples at all in proofs. Not at all. We just have to be careful about how we choose our examples. There's a very nice paper on this, actually, if you want to read this. And another example is the way in which people dealt with existence proofs. So for a long time, existence proofs were really based on providing a specific example of the thing that you wanted to show existed. And then in the 20th century, these non-constructive existent proofs came up. And a lot of people say that this was one of the things where mathematics developed very heavily, because we had these non-constructive methods and they progressively got accepted as part of mathematics. And if you look at these two cases, you would say, well, nowadays we have a different way of doing mathematics. We wouldn't accept something like giving an example for a proof, and we really heavily depend on these non-constructive methods. So looking at this would mean that really it's correct that a modern standard of proofs kind of eliminate the uses of examples. But again, I think if you look at modern proof practices, this is not so clearly the case. If you look at what people are really doing when they give a proof, not only when they develop proofs, but also when they give proofs here. So let's look at proofs by counter examples. Okay, this is a little bit of an easy case, because actually a proof by counter example is not very specific. It's just a negation of a general, statement. So one could say, well, this is not really specification that happens when I give a counter example, because it just tells me that a general statement does not hold. Okay. We have still constructive existence proofs, and they are really still highly regarded. So sometimes if you can give a non-constructive way of proving an existence proof, people will still try to find an example of this, because this tells them more than just having the non-constructive proofs. Of course, we have proofs by induction who use arbitrary examples, and then more general, these without loss of generality proofs that we have. These I would still count as proofs that use examples, these arbitrary examples that we talked about earlier. We can find proofs by example proofs. This just happens. You can find this in mathematical papers as well, where people say, well, this is the general theorem, I prove this for this restricted thing, and then you can see by yourself how this generalizes. This just happens, and people accept this as proofs. Not every time. Again, yeah, people have to be cautious, and they usually are, but this is what happens. Then we have something that are case-by-case proofs, and well, the question is if they're really that interesting because they're a little bit tedious and technical and so on, but still they exist. We have case-by-case proofs. So what they're doing is they are proving something for specific instances of these cases that we have. So I would say that even in modern proof practices, we have use of examples, a little bit more restricted than we had before. And of course, we kind of expect something else from proofs nowadays. We expect them to be fully formalizable, even if we usually don't do it, if we prove something in mathematics or if we write down a proof. But still, we would expect this. But it's not that our mathematical practice nowadays is completely different from the mathematical practice that we had before. There is still a way of doing things that kind of is present in what we do in mathematics here. Okay, let me just... Okay, I have a little bit of time left. And one thing that I would say even more is, of course, if we look at this context of discovery, context of justification distinction, we focus on proofs. But I think one thing that is important and that sometimes does not get talked about when we look at the context of justification is that proofs are not there just as isolated entities in a certain sense. Proofs are built on something that is in a certain sense more important, I think, is namely the mathematical concepts that are used to prove something. And this is something that people have argued for. I have Avigad again here, but you can also find this with other people. He has this proof that the modern understanding of mathematics is not so much as some people would say, well, the axiomatic understanding of proofs, but actually a conceptual one. And this is very much wedded to kind of what are the concepts that we're working with. And the axiomatic approach is one facet of this, but it's not the only facet of doing that. And this kind of opens up, I think, a new area of looking at when we look at justification, because the importance of examples for concepts is much more easy to see and argue for than the importance of examples for proofs. But I think it's there. It's just something that has to be spelled out, and this is what I'm working on right now. Okay, good. I actually was much quicker than I thought I would be, but that leaves us a little bit more time to discussion. Perhaps that's not bad. So I come to the conclusion here. So basically, I want to say the following. So first, that exemplary reasoning is a significant and multifaceted part of mathematical reasoning. We looked at different things that we have here. We have various degrees of specificity and formats. What I mean by this is some can be objects, some can be meta-mathematical, some can be non-objects. And then that exemplary reasoning is use-sensitive. And I think this is really important because there is not one thing that makes an example kind of a good thing, but it's dependent on the uses in which it comes up in practice. We have prominent uses in mathematics that appear in contexts that are usually considered in the context of discovery, so visualization, understanding, arguments for naturalness and usefulness and fruitfulness. And what comes out when we look at these things, at case studies of these things, is that not all examples play the same role. So there are examples that are more valuable or more informative than other examples here. And lastly, even if we switch to the context of justification, we can see that examples are still used in these contexts here. In particular, its use in proofs and proofs contexts is something that is crucial here, and this has to be investigated in more detail. Okay, thank you very much.